just the limit definition of the derivative. And again, this is a function because it's f prime of x, not necessarily the point. And we defined it using the limit as h approaches 0 of the quotient, the difference quotient, f of x plus h minus f of x over h, right? So don't lose sight of this. And as I said, this is the last section that we still, well, take it back. We're going to use that in the next chapter. We're going to use that to develop rules that allow us to calculate the derivative at a much quicker pace. But for the time being, that's what we have. So the first example is the following. We need to evaluate the function. Let's say this is f of x. Let's do two things here. F of x is 1 over x minus 1. And we need to find a couple of things. The first one, what is f prime of x? And the second one is the equation of the tangent at x equal to. So two things. Of course, we're going to use the information obtained in part A to solve part B, keeping in mind that the slope of the tangent is the derivative evaluated at x equals 2. So the first one, we're going to use the limit definition. We're going to write it as f prime equals the limit. And as h approaches 0, because I have a rational function here, instead of dividing by h, I'll multiply by 1 over h. You've seen me doing this before. F of x plus h is now 1 over x plus h minus 1. And, of course, f of x is the original function 1 over x minus 1, like so. And now we need to work this out so that we'll end up having an expression for f prime. So the limit. And since we are subtracting function, if you think about numbers in the numerator, and there are different numbers, and they don't have a common divisor, then the common denominator will be simply the product of the denominator. So the common denominator will be simply x plus h minus 1 times x minus 1. The numerator here, 1 times x minus 1, is simply x minus 1, and the numerator here will be negative x plus h minus 1. So I'm going to change the signs because I'm subtracting, right? So it will be negative x minus h and plus 1. Again, notice the change of signs due to the fact that we have negative 1 times x plus h minus 1. We have some cancellation of the numerator. Let's see, x minus x, negative 1 and positive 1. So the only surviving term in the numerator will be negative h. While we are not going to mess up with the denominator, the reason we are not going to worry about the denominator is, if you think about it, what happens if h is substituted by 0? Well, if you look just at the denominator, if you ignore the 1 over h, if you look at this denominator right here, we don't care. H can be 0, then we have x minus 1 times x minus 1. For all values of x other than x equals 1, this function is continuous. We don't have any problem. It's defined for any other value other than, any x value other than 1. So we are good to go here. Of course, the major achievement is the fact that h and h are being reduced, and now I'm looking at the limit as h approaches 0 of negative 1 over x plus h minus 1 times x minus 1. As I said a minute ago, we can apply direct substitution because replacing h with 0 does not make the function, the argument of the limit, does not make it undefined. So by substitution, we end up having 1 over x minus 1 times x minus 1, or simply x minus 1 squared.
That would be negative.
There is a negative, I'm sorry. You're right. By substitution. Okay? So we have negative. Again, next week, or actually tomorrow, no, it will be next week, we're going to look at a different way to find this derivative without going through the formal or the limit definition of the derivative. But at this point, we accomplish part A. We found a solution to part A, and we're ready to go with part B. And when we are talking about the tangent, we know that the slope of the tangent at x equals 2 will be the derivative evaluated at x equal 2. We're going to write it like so, and this will be negative 1 divided by 2 minus 1 squared. And of course, this will be simply negative 1. So we know that the slope is negative 1. We need a point. The point will be 2 and f of 2. So we need to evaluate f of 2. Well, f of 2 is 1 over 2 minus 1. So f of 2 is 1. So we have m equals negative 1. And the point, let's say x sub 0, y sub 0, will be x equals 2 and y equals 1, like so. And therefore, the point slope formula will read y equals 2 minus 1 times x minus 2, or we are looking at negative x. And here we have 2 plus 2, so negative x plus 4. There was a part C to this assignment that I did not write, and this part tells you to go ahead and sketch the function and its derivative and see if it makes sense. Go ahead. Can I explain how we got negative h? Okay. Common denominator, when you subtract fraction, if the common denominator is the product of the two denominators, then you multiply the numerator of the first fraction by the denominator of the second, and then the numerator of the second by the denominator of the first. The numerator of the second is negative 1. So it means that you need now to change the sign for the first denominator. So it was positive x, it becomes negative x. Positive h becomes negative h, and negative 1 becomes positive 1. And then now you have cancellation. Go ahead.
Back in part B.
Back to part B or forward to part B?
Forward to part B. Okay, I've got the slope. Now, f2, 1, so you got x in 1, 2 and 1.
Mm-hmm.
Now down here, yes, not quite the line equation. Where
That's a modification of the point slope formula. Okay, so recall the point slope formula.
Y minus y
Right.
0 equals
Or form.
slope.
It-
Okay, this
originally it will be y minus y sub 0 equals m times x minus x sub 0, but in calculus, if you add y sub 0 to both sides, you end up having y equals y sub 0 plus m x minus x sub 0. And this is what we're using.
Okay. You got y sub 0 equal to 2. And I'm wondering where that came from.
What, the 2?
You got y equals 2.
Oh, this is 1. Okay. I'm sorry, you're right. Y sub 0 equals 1. So it will be 1 plus 2. It will be 3. Thank you. My arithmetic this afternoon is somewhat deficient. So it's negative x plus 3. All right? Actually, I probably would have caught it when I go ahead and sketch it. That's why it's good to sketch. So let's add part C. So let's read it as an exercise. Sketch f of x and f prime. No, not f prime, and its tangent. So, and its tangent at x equals to, okay? So let me write this out. Now look at the original function, 1 over x minus 1. It has a vertical asymptote at x equals 1, right? And for values of x greater than 1, then it will be positive. For value of x less than 1, it will be negative. So at x equals 1, you have the asymptote. So here's your asymptote. So vertical asymptote at x equals 1. To the right, you have positive values. As we come close to 1, then the denominator becomes close to 0, and the function will shoot up. As we come close to 1 from the other side, let's say 0.9, then we have 0.9 minus 1, it's negative 0.1, and 1 over the negative 0.1 is negative 10. So it will shoot downward, like so. Okay, in particular, at x equals 2, we have 1. So when x equals 2, y equals 1, so we have this point. So the graph passes through this point like so. And the mirror image will be on the left side of the asymptote, like so. Okay, so this is the function right there, y equals 1 over x minus 1. Where is the tangent? Well, the tangent is at this point, and it's negative x, so the slope is negative 1, we know that. This is 1, this is 2, and this is 3. So it has a vertical asymptote at x equals 3, and a slope of negative 1. So this is the equation of the tangent. This is y equals negative x plus 3, or 3 minus x, the tangent. And this is the point, x equals 2, y equals 1. And I made the mistake in the graph. I'm sorry, I need to redraw it. I treat the asymptote as the vertical axis as the y, but this is the y-intercept right here. So really, the slope is too severe. So that's the second error, this class. It's like so. Okay. Let me correct myself here. The tangent is the y-intercept at 3, so this is the equation. This is the line. that is the tangent. Okay? So this point is 3. Like so. I have another one, but it's pretty much the same mechanism. So